Hello everyone. In this video, we will continue to examine topic 7.2, nuclear reactions and the relationship between mass and energy in the context of relativity. So, in the last video, we saw how the postulates of the special theory of relativity led to verifiable phenomena, which are hard to believe but very much confirmed. The phenomena of length contraction, time dilation, and the relativity of simultaneity. So as it turns out, a consequence of that is that any measure of any spatial or temporal interval are relative to the observer of the frame of reference. So, because length depends on that frame of reference and the velocity of an object in that frame of reference, then any delta S, any displacement of any kind, is relative to the observer of the frame of reference. Same for any temporal interval. So any amount of time between two events will be relative to the frame of reference. Now, this has some weird and non-obvious consequences that are can be derived and fully explored, in particular for the conservation of energy and momentum. The conservation of energy and momentum are some of our most fundamental physical principles, and so it really is important that we investigate what happens to them. And as it turns out, there are problems given this. If you calculate the kinetic energy of an object, you'll see that it depends on the velocity of the object, but that velocity is just delta S over delta T for some spatial and temporal intervals. And as it turns out, they don't always translate or transform in the same way. As a result, that kinetic energy is relative to the reference frame. And this has a lot of direct mathematical consequences for which we cannot get into here. But the end result is that it turns out that conservation of energy and momentum both survive this particular problem, but they come a little bit transformed, and as it turns out, they're related to one another. So energy is conserved and momentum is conserved, are related concepts to one another. And that's captured in this long equation here, which you are not expected to know except in the relativity option. And this equation captures the relationship between the energy of an object, E squared, the rest mass of an object, so how much the mass is measured to be when it is at rest in its own reference frame, and the momentum of that object in the chosen reference frame. And in particular, E squared equals m naught squared c to the fourth plus p squared c squared. Okay. Of note is that energy is related to the rest mass times c squared by this factor gamma, equal to 1 over the square root of 1 minus v divided by c squared. This factor gamma appears all over relativity, and you can see how it's the velocity compared to the speed of light that ends up mattering, ends up affecting the energy. Okay, so this is actually the full version of the equation that virtually everyone knows as E equals mc squared. And as it turns out, E equals mc squared is not, without some serious qualifications, always true. You have to be a little bit careful about what you mean by m. So the idea that this equation gives us, though, is mass-energy equivalence. So I'm going to back up for a second and recount what I just said. The special theory of relativity gave us that spatial and temporal intervals are relative to the observer and frame of reference. This threw a wrench in the conservation of energy and momentum. And as it turns out, if you do a lot of math where you lay out the consequences of this, you derive this equation. E squared, the energy of a system squared, is equal to m naught squared c to the fourth plus p squared c squared. Now, consider a mass at rest. what happens if it's not moving at all? If a mass is at rest, then E squared is equal to m naught squared times c to the fourth. Therefore, at rest, the energy of a system is equal to m naught times c squared. That is, in truth, the full form of E equals mc squared. But that m has to be understood as the rest mass, the mass measured in the rest frame, and this equation is only directly applicable to that mass at rest. The consequence of this is that mass and energy are understood to be equivalent. And I'm going to go into detail about what that means in the next video.